What is all the fuss about quantum computing? What is the real state of quantum computers today? What makes them so much more powerful than regular computers? And what would change about the world if they were to become commonplace? Today, we have on a very special guest who's going to help us explore all of these questions and more. So stick around. If you enjoy the kind of conversations we have here on Why This Universe, then there's another University of Chicago podcast network show that you should check out. It's called The Pie. Join host Tess Vigland as she talks with leading economists about their cutting-edge research and key events of the day. Hear how the economic pie is at the heart of issues like the aftermath of a global pandemic, jobs, energy policy, and much more. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. I'm Shalma Wegsman.
And I'm Dan Hooper. In traditional computer science, the most basic unit of information is something we call a bit. At a given time, each bit that's stored in the computer's memory is equal to either 0 or 1. And any body of information can be written as a string of these ones and zeros, as a collection of bits. Computers can manipulate these bits in any number of ways to do different calculations or other operations. And in ordinary computing, the bits are classical objects. They follow the kind of laws of classical physics. In particular, the bits of memory are each at a given time either uniquely 1 or 0. But these days, physicists, engineers, and computer scientists are developing a new kind of computing, which is instead based on quantum mechanics or quantum physics, which allow each single bit to be in a superposition of these zeros and ones at the same time. Today in Why This Universe, we're going to talk about these quantum computers. And to help us do that, we have as our special guest, Henry Lamm. Hank is a theoretical physicist at Fermilab, where he's a member of the Department of Energy's Superconducting Quantum Materials and Systems Center. Welcome, Hank, to Why This Universe.
Hi, Dan. Thanks for that great introduction.
All right. So before jumping right into quantum computers, can you briefly set the table by telling us how classical or regular computers work? And kind of setting up our listeners to understand the distinction here.
Certainly. So at the most basic level, a classical computer, as you say, is built out of bits. And what these bits usually these days is just you have some electrical signal that is either sitting in a 0 or a 1, which is like no voltage is being applied to some electrical circuit, or you have some finite amount of voltage. And then you sort of read this circuit out and say, if it's in the high state, I have a 1. If it's in a low state, I have a 0. And then the way your entire, classical computing infrastructure in the world is built around is just passing very quickly these electrical pulses around and then manipulating them so that these 1s turn into 0s at the right times and these 0s turn into 1s. And as you sort of said already, to set all this up, at all times your, electrical circuit is in some definite state. And it's a matter of you, as the computer scientist or the programmer, writing some code that tells these electrical pulses how they should move around in order to manipulate them in the right way. That at the end of some amount of time, those electrical pulses are in a state that you can sort of measure and say, oh, I've computed the thing I wanted out of them. With these electrical pulses, inevitably the thing we would like to do is build up to something like an algorithm. So we can set some set of rules for some set of objects and then compute something out of them. And sort of the simplest example that people always talk about is what's called sorting, which is you have some sort of array of elements, maybe the integers that are sort of randomly put down in some way, and you'd like to get all of these integers in your array sorted into smallest to largest. So when you have these electrical pulses that are storing all of your elements of your array, what you'd like to do is pass them through a separate part of your computer, like a computational processing unit, which then looks at each element and then does some operation on them. And so the simplest sort of algorithm you could imagine is you pass 2 by 2 every element of these arrays and ask the computer which one is larger. So which electrical set of pulses is largest, and then put that one to the right in whatever structure you've made your array, and then you put the smallest one to the left. And you just keep passing them through over and over again until all of these electrical pulses that are stored in your memory are sorted into ascending order.
Hank, so we have this data stored in zeros and ones, and we imagine writing some sort of algorithms to manipulate those to do certain tasks. that sounds prohibitively difficult. And like, do you have to write a different computer for every possible task? If I want to add numbers together, do I need one kind of computer? And if I want to sort things in a certain order, do I have to use a different kind of physical device?
So, of course, you'd like to hope not. And this is sort of the notion that people long ago that, you may have heard of called Alan Turing came up with this proposal that if you design the computer to be sufficiently flexible, you can have what's called a Turing machine, which is a device that's capable of simulating any other device that you might want. And anything you could possibly imagine computing, a Turing machine is able to compute as long as you're willing to write sufficiently complicated code. So there isn't a need to redefine or rebuild a new device every time if you want to do general computation. Now, of course, these days we are sometimes interested in not having a computer that can do anything because a specialized case might be able to be designed much, much faster. And this, in fact, is what FPGAs are often used for in industry. But your, laptop in front of you, in principle...
What's an FGPA?
An FPGA is a field programmable... Now you've put me on the spot and I have to remember what the other ones are. Gate array.
Okay.
Yeah. So let's try this again. So an FPGA is a field programmable gate array, which instead of being, as I sort of said, like your laptop or your cell phone, that in principle is infinitely flexible in what it can compute, these electrical circuits that you would use for your computation are aligned in a very specific way so that they can do one task very, very, very efficiently. And if you'd like to do a different task with them, you actually have to physically move around hardware or physically recode the thing in order to get the advantage you would have.
All right, so on the one hand, we have kind of the universal computing machine, the Turing machine, which is kind of the infrastructure model that we use to build our laptops and cell phones and things. But then for maybe specific, maybe industrial applications, you might do hyper-specialized kind of hardware that can do certain calculations very efficiently, but maybe can't do other things. Is that about right?
That's exactly right. And this shouldn't seem so foreign maybe to some of your listeners in the sense that the reason you have a CPU in your computer and a GPU in your computer is exactly the same reason. It's that certain calculations can be done much faster if you specialize to them. And so it's sometimes worthwhile to design devices for that. In fact, this is part of why sort of the machine learning and the artificial intelligence boom of the last few years has been possible, is that there have been very specialized computing units designed for those tasks.
If it's not too difficult, could you give like one sentence about what the difference between the CPU and GPU is?
Yeah, so in the case of a CPU and a GPU, a CPU is by definition supposed to be something that can compute essentially anything you would need to do. So it has no specialization in that sense. In contrast, a GPU used to stand for graphical processing unit. So they were specialized to doing the graphical output from your computer to your display so that you could actually see things. And it turns out that the types of calculations you need just to visualize things on your monitor can be optimized in such a way that you most of the time are only doing sort of integer addition and multiplication, division and subtraction, as opposed to needing arbitrary types of computation. And so when you restrict yourself that way, you can do things much faster. And it turns out that those same simplifications that make visualization really good are very, very good for doing artificial intelligence.
So the AI computers are more similar to the GPUs.
Right. And in fact, this is why if you've tried to build your own computer recently and there were a whole bunch of skyrocketing prices in GPUs, while it used to be cryptocurrency that was causing these big booms, nowadays it's the AI companies all want to buy these GPUs.
So in a classical computer like you're describing, all those bits are uniquely ones and zeros. They're either their voltage is on or their voltage is off, and it's all very uniquely one or the other. Let's use that as a jumping off point to explain how quantum computing would work differently.
At the fundamental level, the difference between a classical computer and a quantum computer is that instead of having a bit, as you say, that's in a definite state, you're allowed to have some object that is going to be a qubit, which is allowed to be in a superposition of two different states. And so, whereas in our example of a classical computer, we're talking about sort of macroscopic voltages being stored in a device, the more typical piece of hardware that you think about when you do a quantum computer is you have sort of a single spin or a single electron or a single photon that's in some set of states that you're going to talk about. So you're sort of talking about the way fundamental particles behave and then storing the information in their state. And because you're talking about a quantum object, you're allowed to invoke things like, I'm not going to be in any single fixed definite state. I'm allowed to be in some superposition of all the states that these fundamental particles can be in.
So the example I like to give when explaining superposition to people, and we talked about this on our long time ago episode on our tour through quantum weirdness, if you recall that one, Shalma. But I like to think of like a coin is, either going to be heads or tails, but you could imagine a quantum coin, which, at least until you measure it, is in a combination of heads and tail states. Instead of being heads or tails, it legitimately is heads and tails at the same time. And that's analogous to what a qubit is in a 0 and 1 state at the same time.
Right. And that's a great example.
We have this classical computing thing, and then we have what sounds like a harder way of doing computing using qubits on a quantum computer. Why are people so interested in doing this? Like, why not just stick with classical computers?
Right. So that's a great question to ask. And in fact, it was the thing that people asked in the early 80s when this topic was even brought up. The first people who sort of actually talked about quantum computers were actually asking a sort of interesting computer science question, which is, okay, I can do classical computing with electrical pulses, as I just said. They asked the question, well, quantum mechanics is different in that on top of being about superpositions, it's also about always having probabilities that are fixed as a function of time. You can't sort of force a set of ones to all turn into zeros. And so they asked the simple question, which is, if I had a quantum mechanical system, could I do the exact same thing as a classical computer? And after a lot of work, people eventually discovered that, yeah, if you tried to use quantum mechanics, you would be able to do all the same computations as a classical computer. And it wasn't until a little bit later that people, including Richard Feynman, pointed out that, in fact, there are problems where a classical computer will be very slow to solve the problem you might want to do. And in fact, if you could build a quantum computer, they would be faster. And for Feynman, the first example was just if you would like to simulate a different quantum mechanical system. So, for example, in my work, if you wanted to collide two particles together and compute what the cross-section would be for this thing at the LHC, that is a problem where a quantum computer would be expected to be better because you can take advantage of the fact that a quantum system can better simulate another quantum system than a classical one can. And so for quantum computing, this became an interesting thing for physicists to think about because it would allow us a new computational tool to do theoretical physics predictions with. But it wasn't really until the early 90s when Peter Shor came up with his algorithm that sort of the more general public became interested in quantum computing because he demonstrated that there was something sort of outside of the realm of quantum systems simulating other quantum systems that could be sped up and have a real practical impact on the world.
So let's back up there. There's a lot to unpack, and I'm personally pretty curious about some of the things you said. So you said if I want to calculate the cross-section for two scattering particles or something, it would be efficient to use a quantum computer. But like, I learned how to do that in grad school, and the textbooks I learned how to do those calculations from didn't mention any quantum computing. In fact, it could all be done on paper generally. So what am I missing? Where does the quantum computing come in?
Yeah, Dan, how efficiently can you do that on paper?
Not very much anymore. I was really good at it once.
For audience reference, a cross-section is basically just the probability that two particles are going to collide, right?
Yeah. There's at least proportional to that, yeah.
Right.
Yeah. So I agree, Dan. Similar to you, in graduate school, I learned how to compute some types of cross-sections. But the ones we almost always learn in graduate school are what are called perturbative calculations, which is where there is some small parameter in your calculation, and it's typically sort of the interaction strength between the particles that's sufficiently small that you can consider a series of smaller calculations that if you added all of them back up together would give you the full thing you want.
Right.
So the obstacle is that when you want to do things like particle collisions at the LHC that's working today, you don't necessarily always have a small parameter. So in fact, if you want to collide two protons and produce the Higgs boson, there are a whole bunch of places in that calculation where there is no small parameter to help you. And it's at that exact point when you have to rely on computers, either classical or quantum, to help you out.
But as Feynman showed, the quantum computers can do that faster, at least in principle.
Right. And when I say that Feynman sort of suggested you could do it faster, for the type of problem we're describing at the LHC, the difference is a quantum computer could maybe do it in a couple of years, whereas you have no expectation if you used all of the resources that humanity has to bear in classical computing, you would ever get the right answer.
Oh, okay. So dramatically
It's really that large of a difference.
Oh, wow. Okay. So you would have to have a quantum computer running this calculation for a few years in the background anyway to learn these facts of fundamental physics.
If you wanted to compute something that large, yeah, these are hard problems no matter what you do.
So I'm not an expert on this at all, Hank, but I've heard that there are certain mathematical operations, algorithms that are, pretty straightforward or simple to understand that illustrate the advantages of quantum computing. Maybe you have one or two of those in your pocket you could share with us.
Prime number factorization is the canonically good one, I should say. So let's take a try at that. So prime factorization says if I have some very, very large number that only has two factors other than itself and 1, and these two factors are both prime numbers, therefore, what are those two numbers? And if you have a very small number, so if you add, for example, the number 15, it's probably relatively easy to figure out that the prime factors of 15 are 3 and 5.
Right.
But as you keep choosing larger and larger numbers, as you go to like 131, as you go to 2,963, it becomes harder and harder to see what these factors should be off the top of your head. And it turns out that a classical computer also gets slowed down in terms of how quickly it can do this. And what was shown by Shor is that if you have a quantum computer, that quantum computer can in fact find those prime factors for you exponentially faster than a classical computer would. And while this might seem like some sort of esoteric math topic to just say, oh, congratulations, you can do a clever party trick by factorizing a number quickly, this exact idea of the difficulty of prime factorization is what many types of public cryptography rely upon in order to keep us secure today in our banking records and our, secret medical information. And so this previously believed to be somewhat esoteric mathematical algorithm all of a sudden becomes incredibly important if you want to have secure communication and secure internet usage. And that's sort of what really spurred the quantum algorithms and quantum computing was this algorithm's utility.
So when I, use my credit card online or something, presumably they're passing that number back and forth using this prime number factorization scheme, right? So some intermediate party can't just learn my credit card number. But let's say that intermediate party now had a pretty good quantum computer. They could probably break that apart in no time, right?
So the question of no time is relative, right? The bigger your computer is, the more quickly you can do it.
Sure.
Sort of the state-of-the-art research today is in fact on exactly how big of a quantum computer do you need and how long would it take to run in order to come up with this number. And there are sort of papers that have come out in the last 5 years sort of suggesting that for the level of security we have today, if you had a computer that had something like 1 million qubits and you ran it for about 7 hours, you would be able to get your single cryptographic signature cracked. So it's not like you can break the entire internet instantaneously. It still takes you some time because you have to run them one by one. But 7 hours for your banking account, I think, is not an amount of time anyone would be terribly comfortable having around. And as those computers get bigger, that number comes down.
Yeah. So that's 1 million qubits. Now, for comparison, like what's the state of the art in a real world quantum computer today?
So in a real world quantum computer today, if you're talking to industry partners and people like that, you can get up to about 100 that you can play around with.
Okay. So we're still 2 orders of magnitude fewer qubits than it would take to even hack, one credit card number in 7 hours or whatever.
I think that's 3 orders of magnitude, I hope.
Oh, yeah. Sorry. 3 orders of magnitude. 3 orders of magnitude away. Okay.
Yeah. And there's another important fact about this, which is I told you that if you gave me 1 million qubits, but these qubits have to be relatively noise-free. Mm-hmm. And so this is sort of what keeps you from having larger quantum computers. Like, I have a colleague who loves to say every classical computer is secretly a really terrible quantum computer because you're never really able to manipulate the actual superposition in it. But it really is a quantum system at the bottom of it because the whole world we sort of think is quantum mechanical.
Right.
So sort of the obstacle that sort of has this scaling going on with these companies and researchers around the world is how can I keep a sufficiently large number of qubits that are reliably quantum? And so it's this notion that I can sort of build for you 100 qubits and you're allowed to manipulate them in quantum mechanical ways. But if I tried to build the same system with 1,000 with today's engineering and technical know-how, they would be so noisy that you'd never be able to do any quantum operation on them. And so you need not just to go up 3 orders of magnitude in the number of qubits, but you need to also reduce the noise even from what we have today on those 100 qubits in order to make these computations possible.
So with ordinary classical computers, the computational power has, famously grown exponentially, this Moore's law behavior of doubling in computation speed every so many months. Is there something analogous going on in quantum computing? Is the number of qubits we can manipulate in a single quantum computer growing very quickly, or is it growing more slowly, or is it not growing at all?
Right. So depending on who you ask, maybe within the last 10 to 15 years, the first 2 qubit systems at all existed. So in some ways, there's been infinite growth in the last, 20 years. But as of late, something around sort of Moore's law, except every maybe 2 to 3 years, as opposed to 18 months, which is what Moore's law is usually stated as, has been the trend. But again, that should be caveated by, Moore's law is a plot that goes over many, many, many orders of magnitude that sort of it worked out with. Yeah. Whereas, the fact that qubits are doubling every 2 years is only saying you went from 2 to 4 and 4 to 8. Like it is somewhat artificially faster just because it's so much smaller systems you're starting with.
So quantum computing is kind of like what classical computing was like in the 1950s or something. Just, just barely getting started, kind of rudimentary. You're hoping these trends would continue, but you don't know if they will, et cetera. Yeah.
Exactly. And there are a lot of obstacles that people have already foreseen will need to be done to scale up because of what we learned from the classical computing history.
So right now, quantum computers aren't able to decrypt my credit card number that they intercept on the internet. Are there any real world practical applications that quantum computers are useful for, that can in the sense that they can outcompete resource for resource classical computers, or does that not exist yet?
So this is in fact an incredibly controversial topic at the moment about whether we've hit that point or not. Because, of course, once you have something that can do anything interesting and anything useful faster than a classical computer, this changes the entire state of quantum computing. So to back up and say a little history here, once upon a time, people talked about quantum supremacy, which was the idea that a quantum computer is so crushingly better than a classical computer that you would never use the classical computer at all for this, for a particular task. Then people sort of, both because the word supremacy has some ugly history to it, and also because they thought that it was a little impractical to just demand that a quantum computer crushingly defeat a classical computer, they chose the word quantum advantage, which is this idea that a quantum computer is substantially better than a classical computer.
Sure.
And then in more recent history, people have sort of pivoted to the idea of just quantum utility, which is the idea that if you were a person trying to solve a problem, would you choose the quantum computer or the classical computer to solve the problem? And so you can imagine with each one of those 3 choices, you're sort of asking for the quantum computer not to be nearly as overwhelmingly more powerful than the classical computer, but just that at some point you would choose it over it because it's easier for you to do. And even right now, I would say it's not clear that the quantum computers are sufficiently large in terms of their number of qubits and noiseless enough in terms of their behavior that we've demonstrated anything that even that bare minimum of I would choose the quantum computer over the classical computer has happened yet. But at the same time, people should be, excited, and people have been, and there have been news articles written in the last couple of years about so-called quantum advantage or quantum utility, making claims about it. And then both times that these big claims were made, someone within the next few weeks came out with a classical algorithm showing that they can do it just as quickly, or they can do it reasonably quickly. And so sort of those particular claims have died down. And these were big companies making these claims. Like Google made the first one in 2018, and then IBM just this year made a claim as well about having something with quantum utility. And both times, clever people with classical computers came back and showed that they could do the same thing.
Oh, okay.
So the next probably 3 to 5 years, we will finally see a real demonstration unambiguously of sort of quantum utility, which is, where you would prefer to use the quantum computer over the classical computer. But in the meantime, I expect there to be lots of claims of it, and then they go back and forth as the classical algorithms get better too. Because you're always sort of playing at the knife edge of which one you want to use. And so if you're not sufficiently clever on one side, you may miss some speed up that you could have been hoping for to help you out.
So we've got a few years and we'll start seeing legitimate quantum utility I don't know. Are you saying a few years after that and we'll have quantum advantage on the regular? Is that kind of how I should extrapolate?
Yeah, I think that's true.
And in 10 or 20 years, when, I get out my cell phone or whatever device we're using then, and I calculate something, will it use a mixture of classical and quantum computers? Will everyday technological usage be permeated with quantum computing?
So that's a really interesting question. And the real statement is that we don't know. So whereas sort of in the 40s and 50s, people talked about classical computing and they sort of said, oh, this will never be something ubiquitously used. It will always just be these large scale devices that universities and national labs and people need. We can clearly see that turned out not to be true because as you referenced, your cell phone is in your pocket probably, and it has an immense amount more computing power than any of those things had back in the 50s. But the subtle difference is that while quantum computers can do some tasks much, much faster, they don't do everything faster. In fact, there are some tasks where sort of if you actually timed them, would be probably slower, but in practice, you could implement them on a quantum computer. In particular, for example, the thing I gave earlier about the idea of sorting to elements of an array and then getting the entire array sorted, this is known not to be able to be done faster on a quantum computer. So there's no reason you would ever want to offload that particular calculation. So at the risk of being defeated by history, I'm sort of skeptical that there will ever be a need for the day-to-day person to have a quantum computer in their pocket. But in fact, there will be sort of a very limited number of applications to it. And the way we will solve those problems is by having large data centers somewhere that have large quantum computers for us, or a national lab or a university sort of is building their own special purpose for research and things like that.
So it's possible that one day in the future, the big companies have, like Google, Microsoft, they have giant quantum computers that were all kind of like through the cloud sending certain sorts of calculations to certain sorts of computations.
Yeah, that's sort of what I'm imagining today. But again, this is all caveated by the idea that I've not seen anything where like the general public uses some underlying calculation all the time. It's not the same way with, as I said, like sorting or, you trying to look at your cat pictures does not require quantum computation to solve it. That's really something that you can do perfectly well with a classical computer.
Unless it's Schrodinger's cat.
Yes, there you go.
Sorry, that's an awful joke.
Yeah,
I feel bad. I feel bad about that.
But in contrast to sort of classical computing, where basically anything you would ever want to do, you could imagine writing code for it and it being faster than you trying to do it by hand. Sort of the number of algorithms that a quantum computer can do faster than a classical one is maybe, somewhere between, 50 and 100. And there's a nice website called the Quantum Algorithm Zoo that just lists all of them that are known today and how much faster they're expected to be. And so they're typically these sort of relatively complicated mathematical problems that mathematicians and physicists are sort of interested in solving, but they don't always map nicely onto some real world application. And Shor's algorithm is in fact the perfect example. That's like what that algorithm actually is at its fundamental level is that if you had some unknown function that is supposed to repeat itself after some frequency of time, how can you find that frequency quickly enough? And that doesn't even at all sound obviously connected to the prime factorization I talked about, but it turned out that Shor cleverly found a way to connect these two. And so whether these known algorithms secretly have some, killer application in today's world for doing the coolest video games or, making banks more efficiently be able to trade things isn't guaranteed, but it's not prohibited either. And, as these computers become more and more real, more and more people will spend time thinking about them and they may discover more applications like Shor's algorithm that really do have an impact on everyone's day-to-day.
So is that list of algorithms that quantum computers have an advantage at, is that growing quickly with time? Like 10 years ago, was the list a lot shorter?
I wouldn't say it was a lot shorter, no. I would say anytime a new quantum algorithm is found, there is still excitement in the community. So
it's still a big deal.
It's still a big deal when you find something that genuinely is new and that's faster. And again, because this is right at the intersection of like theoretical computer science, physicists, and mathematicians, the extent to which a quantum algorithm is faster, who believes it and to what extent they care differs. A mathematician or theoretical computer scientist may demand that you give them a rigorous proof that this thing asymptotically has the right structure through 1,000-page proofs, whereas a physicist might say, that seems likely to be faster. I would probably try coding that instead.
Mm-hmm.
So we've been talking a lot about quantum versus classical computers, why people are excited about this. I kind of want to backtrack and talk a little more about the challenges of building a quantum computer. We've kind of mentioned this issue of noise, right? So could you explain more about what that means? Like, what exactly is the noise we're dealing with, and what is the challenge with quieting it?
So the easiest way to think about why this is difficult is that for most of human existence, we didn't know about quantum mechanics. Most of the time, we thought that the classical world was the true way to describe things. And that's really because sort of at large scales and at long times, the quantumness of a state becomes very hard to see at the sort of macroscopic level. It's only, when humanity started probing down at the atomic scales and the, nuclear scales that we discovered that no, all of Newtonian physics kind of falls apart on us and we need to do something different. And so the difficulty of building a quantum computer is exactly that, is that you need to preserve the quantum mechanical nature of something at very, very large scales and with very, very fine control over them. And for example, one thing that you have to worry about is the fact that the state of your quantum computer can sort of decohere, where the idea of decoherence is if you have a quantum state that's in some superposition and you just left it alone, it will interact with the environment because there's a temperature to the universe, as I think many of your listeners probably know. There are random particles flying in from outer space at all times that are going to hit this thing and interact with it and cause it to fall out of its nice, pure, separated quantum state into something that looks more like a classical system where it's just the bits now sitting there again. And so sort of the very most basic step of designing a good quantum computer is you have to find a way to isolate it from the environment, except when you would like to send your pulses into it to manipulate it. And if you can't control it when you want, but not allow the rest of the environment to mess with it, you're not able to keep it in a good quantum state and take advantage of it.
So we're kind of implicitly talking about entanglement a bit here, right? So in a quantum system, one of these features of quantum mechanics is that two particles can become entangled, right? So the state of one particle depends on the other. Maybe these are two particles that were created at the same time or interacted or something like that. And so in order to have full control over the quantum system, we have to have control over all the particles that are entangled together, right? So if we're letting other things hit our quantum computer, like even just light or something like that, right? A muon from space or whatever, that's going to entangle with our quantum computer, and we're no longer going to have control over the whole system, right? Is that one way to think about it? Okay.
Right. And these are the same types of problems you worry about in a classical computer too. Like we worry about cosmic rays hitting our regular computers when we send them out into space that we have to radiation harden them for. It's just that the problem is much more acute in that you need to be keeping this computer in the state you want it in at a much higher level in order to keep that entanglement preserved.
So how do you do that? Yeah.
Yeah. So, the way you do it today is you put them in sort of the coldest environments we can design. There are so-called helium dilution refrigerators, which literally uses liquid helium to pull out as much energy as humanly possible from these things so that they're in a very, very cold state. And then you shield them from the magnetic field of the Earth by putting them in some metallic cavity that protects them from that. Then you have to design very, very special electronics that are very, very low fluctuations in terms of the differences between the pulses you try and send in and the pulses that you actually get from these devices. You try and minimize the cable length that you end up passing through because, as these cables get longer and longer and longer, there's the fact that the cable itself has a resistance in it that can mess with you. So it's really about sort of designing the cleanest room possible, not just from, bacteria and dirt, but also electronic noise and radiation from the outside environment. And in fact, some of my collaborators in the SQMS Center actually took one of these quantum computers and they put it underground to study how the fact that there are cosmic rays at the surface of the Earth that are less detectable underground, to see if this actually made an appreciable difference in the fidelity of these computers.
And did it?
Very slightly. It turns out that cosmic rays are not our leading source of noise at the moment.
Right. First we gotta get rid of just normal, photons and stuff, right?
Right. Because a lot of these computers today are built off of just superconducting circuits that are on top of silicon, the same way that we have semiconductor computers today. It's a very, very similar technology, except for you need them to be superconducting.
Mm-hmm. And how cold are we talking? Or how close to... We're trying to make this as close to absolute zero as possible, right?
That's right. So We're always trying to get these computers as cold as we possibly could because it would just make our lives easier from one source of noise, which is sort of thermal noise. But we're talking, millikelvin devices typically. As you could imagine, getting some relatively large volume held at millikelvin temperatures is not the most easy thing to do. And in fact, a huge limitation in terms of doing quantum computing R&D is the fact that we don't have enough sort of cold volume to put these devices in and study them. And so as part of SQMS as well, we're trying to build the world's largest helium dilution fridge, which is going to have a few cubic meters worth of millikelvin temperature, where you could imagine putting in larger devices that have a lot of their control as close to these chips as possible in order to minimize cable length and thermal changes and other noise like that in order to make these things better. And around the world, in fact, a bunch of companies that are building quantum computers are sort of slowed down by the fact that there aren't enough dilution fridges in the world to use. And so this entire question of how do you cool these things down is an active piece of quantum computing, research as well.
Yeah, I mean, it seems like there is this just like fundamental challenge where we're trying to interact with an inherently quantum system in a macroscopic way, right? We want like information that we actually need and like interact with on our scale to kind of transport itself through a quantum system.
That's precisely what we're asking to do, which is exactly also why it's hard. Another one of these big challenges is not so much designing, one device that in principle has 1 million qubits. Now, making them noiseless enough is difficult, but how do you get 1 million quantum mechanical signals out to a classical computer that you can then understand what signal you've gotten and use it usefully is a whole nother section of what people with doing quantum computing research work on, is the actual classical so-called control and measurement systems out from the quantum computer, because this is, an immense amount of data, as you can imagine, just, 1 million, qubits of worth of information that you have to read quickly, interpret, and then send back in order to implement new controls on these algorithms. And so you can imagine having classical supercomputers sitting there just being used to manipulate the quantum computer as it goes.
Are there any common misconceptions you hear about quantum computing?
One of the biggest misconceptions is that these quantum computers are going to speed up everything, that they are going to just radically change the world because all of a sudden everything must speed up with the quantum computer. And as we sort of discussed earlier, that's not the case. It's that there's sort of a limited number of places where these things are expected to be much, much better. One thing maybe worth saying is that we spent a lot of today talking about what a quantum computer is and how it will maybe speed up types of computation. But in talking about how difficult it is to control these machines, sort of high energy physicists and theoretical physicists like myself got interested for a somewhat separate reason, besides that it will help us do new interesting calculations. But that if you're really asking, can I control this system at such a high precision to do these calculations, you're really saying that we think we understand how quantum mechanics works to such a level that this is possible to engineer. Like in the same way that the only way you know that you really know something is to teach it, you really only know if you understand something when you can build it and reproduce it. And so there's a lot of hope within my community that we could learn a lot about the fundamentals of quantum mechanics and what is, perhaps beyond it in terms of quantum gravity or something like that by studying these machines just in and of their own right about how they should be behaving. So it's not solely necessarily, an engineering and a computational, task to go to the future. It's really about learning how is it that our universe works at a fundamental level. And people write papers about, well, if a quantum computer doesn't behave quite like we think it should at the most high precision levels, that could give us information about really what's going beyond the standard model, what's going beyond the physics we understand today in ways that are inaccessible in some ways in any other type of an experiment.
Yeah, so if we do get a working quantum computer big enough, humanity will have come far from the nobody understands quantum mechanics quote of the 20th century, right?
Yeah.
Right. I think fewer people will say that if we have a large-scale quantum computer.
Why This Universe is brought to you by the University of Chicago Podcast Network. It's edited and produced by me, Shalma Wegsman, and my co-host is Dan Hooper, a professor of astrophysics at the University of Chicago and Fermilab. If you like our show and you want to support us even more, you can find us on Patreon. There you can access ad-free episodes of the show, as well as exclusive Ask Us Anything episodes where you get to ask Dan and I direct questions about physics or anything else. So if you are curious about that, you can find it at patreon.com/whythisuniverse. Thank you so much for listening and for your support.